Good morning, children. I hope you have seen the previous videos which I have posted on ionization energy and oxidation state. Okay, so please watch that before you attend this particular lecture. So today we'll be talking about electrode potential variations in D block elements. Now first let's understand what is electrode potential. Electrode potential is the ability of the electrode. Particularly we are talking about D block element, that is the metal. So ability of the electrode, that is a metal, to undergo oxidation or reduction. That means if we know the value for the electrode potential, we will be able to judge which oxidation state is most stable. Right? So this you represent as E. At times you'll also find it's given as E naught. If it is given as E naught, it is referred to as standard electrode potential. Standard electrode potential. Right, this naught stands for standard electrode potential. Now what is the standard electrode potential? It is the electrode potential which is measured under standard conditions, that is 25 degrees Celsius, or you can write 298 Kelvin in terms of Kelvin. And if the concentrations are there, it should be 1 molar. And if the pressure for the gases, then it is 1 atmosphere. So we mainly focus upon these two, concentration and the temperature. So under the standard conditions, what electrode potential is measured, this is referred to as a standard electrode potential. Another point, children, you will find like that many a times written as, say, E naught M N plus slash M. This is a reduction electrode. This is a standard reduction potential. This is what? This is standard reduction potential. Now why this is reduction? You can just see here that this is plus, oxidation state is positive, and it has undergone reduction. From plus something it has become 0. If only M is there, means it is 0. So from some positive it has become 0, that means it has undergone a reduction. For example, you can see, say E naught, say Cu2 plus Cu. This will be read as standard reduction potential of copper, and the value is 0.34 volt. Right? And if I talk about zinc, it is Zn2 plus Zn, and the value is minus 0.76 volt. Okay, this is standard reduction potential of zinc. Now at times, suppose you are asked to write down the oxidation potential. Oxidation potential would be written in this manner: Cu slash Cu2 plus. It will be increasing. From 0 it has become 2 plus. This is oxidation potential, standard oxidation potential. The value will remain the same, but only thing is now it will be in the negative side, but the opposite side. For zinc, if it has to be there, it will be this Zn slash Zn2 plus, and the value would be now plus 0.76 volt. So please read carefully whether it is reduction or oxidation potential. But more commonly, as that electrochemical series, it's mainly given in terms of the reduction potential. That is the standard format we follow. But at times, in multiple choice or competitive exams, note this, whether it is oxidation or the reduction mentioned. Right? Another very important point is what we have studied in electrochemistry chapter, that this E naught value, I've already explained there also, just check it, more negative, or you can say less positive. Either way I'm saying, or generally at times they will say lower electrode potential. I'm specifying this so that you understand better. More negative electrode potential in case both are negative. If both are positive, less positive. Or generally you can say lower electrode potential. That means it has tendency to act as anode. Anode means it will undergo oxidation. Oxidation means it will act as a reducing agent. It will act as a reducing agent. This is very, very important. More negative. Now let's compare these two values which are given over here. Out of these two, more negative is this one. The zinc is more negative. More negative means out of these two, zinc will have the tendency to undergo oxidation. It will act as anode. That means for zinc, out of Zn and Zn2 plus, which is more stable? Zn2 plus is more stable because it is having the tendency to undergo oxidation. Why? We are going to discuss all that. Factors are there and also on the basis of the configuration. This is having more positive. Out of the two, this is more positive. Positive means it will act as cathode. It will undergo reduction. That means for this, Cu will be more stable than Cu2 plus. So in a way, I can also write like that. More positive, or you can say less negative. Or in other words, you can say high electrode potential value means it will act as cathode, will undergo reduction, will also act as an oxidizing agent. If it is undergoing reduction, obviously it will be acting as oxidizing agent, right? And vice versa. If it is undergoing oxidation, reducing agent, reduction, oxidizing agent. This is very, very important to understand that E0 values, why it's more negative, positive and all that stuff. Another thing, the important is you will find that in D block elements there are irregularities. There are the E0 values. The E0 values are very, very irregular. Why are they irregular? What is the reason for it? There are various factors. Okay, let's first see the graph. Just check this graph. This is a graph between standard electrode potential value and 3D series. That is starting, they have given from titanium, vanadium, chromium up to zinc. So what you find is, this is, the M2 plus slash M. Means from 2 it is becoming 0, that E0 value is given. That depends which, the change in the oxidation state they are considering. So you find that it is generally increasing. This way, as the atomic number is increasing, the E0 value is increasing. This is 0. 0 is for hydrogen. Okay, so what you find is generally it is increasing, but there are some exceptional cases. You can find Mn. Mn is comparatively more negative. Why it is negative? We'll be discussing. Zinc is more negative. Then you find nickel also comparatively down. Cobalt is also little down. Copper is positive. Copper has gone beyond that 0. Why? Why these values are, some are positive, some are negative. To understand that, let's consider the factors. There are 3 main factors, which are responsible for the E0 value. Let me start with some element M, that is solid. That solid M is to be converted to gas. Now what is that is to be converted? Whenever we are talking about that electrode potential value, in the solid form it is not going to act as oxidizing agent or a reducing agent. It has to be in some solution. You'll be immersing it in some solution, in that it will be acting as oxidizing or reducing. So we need to consider all the energy transitions which are taking place. So M solid, that M stands for any transition element M, solid has to be converted to gas. Gas is then to be converted to ion, also in the gaseous state. This M ion is to be then converted into M plus aqueous. I am considering thing plus only, but at times it can be 2 plus, 3 plus or whatever, what example we are considering. So I am just talking about the factors as of now. On what factors this E0 value depends. Why for some it is positive and for some others it is negative. So there are 3 main factors. Now what is the process occurring here? Let's see. Solid is converted to gas. This is sublimation. This is plus sublimation. Why it's plus? Because it's endothermic. And at times, they are also referring this to as enthalpy of atomization. Basically, from solid, it's converted into gaseous atom separately. So it's enthalpy of atomization. This is endothermic. Then further, this gas M is to be converted to ion. That means we are removing electron from M and forming an ion. Even this is positive, it's endothermic reaction. This is plus ionization enthalpy. So far 2 energies we have considered, both are endothermic. Right, the last one is M ion in the gaseous state is to be converted into M aqueous. That means it's water. So in this process, the ion is getting hydrated. So when it is getting hydrated, the energy released will be hydration enthalpy. So the last one is negative. It is minus hydration enthalpy. It is minus hydration enthalpy. So what it is, plus, this is enthalpy of atomization, it is positive. So enthalpy of atomization, I'm writing why, it's positive sign, right? Plus ionization enthalpy, that is also endothermic. This is minus. Actually, we are all adding because these two are endothermic and this is negative. So I'm writing in this format. The sum of all this will give you the total enthalpy which is liberated. This delta H overall will now decide whether the E naught value will be positive or negative. In case you have these positive values more, enthalpy of atomization, it is atomization, enthalpy of atomization, and if ionization and values are more than the liberated one, then you will have the overall, that E naught value positive. In case you find that the hydration enthalpy is more than the sum of these two, then the overall value will be negative, then the E naught value will be negative. So it is basically the sum of these three enthalpies which is going to decide whether the electrode potential will be positive or negative. Okay. Now listen children, this is very, very important. You will be getting questions on the basis of why the E naught value is more negative for so and so element and why positive for some elements. So which all elements? You can just see the values first. So we will be talking about Mn, why the value is more negative. Okay, then nickel is also negative, zinc is also negative, copper is positive. Why these four values are given? This is in terms of 2 plus / M. Okay, so let's discuss the reasons for it. Okay, so I've just jotted down here. So we'll be talking why for copper it is more positive. So in a way, this is from Cu2 plus to Cu, means out of these two which is more stable, that is what we want to refer to. So as I said earlier, if it is more positive means the lower one is more stable. If it is more negative means this is more stable. For more negative, this is more stable. For more negative, this is more stable. This is what I already mentioned it. Okay, like I mentioned it here. Okay, more negative means it will undergo oxidation. More negative means higher one is more stable. More positive means the lower oxidation state is more stable. So keeping this in mind, we will explain. Now let's see this one. This is more stable. So we can explain it this way. Suppose Cu is first converted, that solid is converted to Cu gas. Okay, that gas is then converted to Cu. If I remove both the electrons in one go, say at a time one only is there, but I'm just writing both the electrons remove. This is there and now this is in the aqueous, right? Okay, so what is the energy here? Enthalpy of atomization, which is positive. This is ionization, which is positive, and this is hydration, which is negative. So why is the value more positive? You will write the answer. It is more positive because the positive components are more, or probably we can say the negative components are less. So for this you will be writing here as the sum of these is higher and this value is low. Okay, so for copper you will be writing, so low, no, high. It is high enthalpy of atomization. High enthalpy of atomization, or in other words we can say more sum of enthalpy of atomization and ionization. This value is more, positive value is more, and low hydration enthalpy. So every time I'll not write down this whole thing, that state change, so I'll just write down in terms of the energies. Okay, so for copper, why it is positive? Because of high enthalpy of atomization and low hydration enthalpy. Now this value is more negative. One thing we know, more negative means the positive, that higher one is more stable out of this. This is 0. Out of 0 and 2, which is more stable? This one. You can also explain this, on the basis of the configurations. Okay, just check it. Mn is solid. Mn solid has formed Mn gas. That Mn gas has formed Mn2 plus gas, and now this has formed Mn2 plus aqueous. So what is the configuration of Mn here? This is 4s2 3d5. And what is the configuration here? 3d5. After losing both the electron, it is 3d5. So out of this and this, which is more stable? This one. This is half filled in the valence shell. This is more stable. So its ionization enthalpy will be comparatively less because it can lose these two electrons readily and acquire more stable this one configuration. So you will write down for this Mn the low ionization enthalpy. Ionization enthalpy is low so that it is getting the half-filled stable configuration. The same is the case of zinc. Zinc configuration is 4s2 3d10, and when it forms Zn2 plus in the gaseous state, it is now 3d10. So its positive component will be less because its ionization enthalpy will be less here. Okay, so this is comparatively less. So 2 electrons will be lost, means now it will have 3d10 in the valence shell, which is more stable for zinc. Okay, so here in these two particular examples, you need not talk about hydration enthalpy. For these two examples, you will write down half-filled and full-filled configurations are more stable, so it will like to lose the electron and acquire them. For nickel, that configuration is not, that will not be fitting into, because nickel configuration, if you write down, it is 4s2 3d8. After losing, it's not getting that half-filled configuration. So why it is more negative? It is more negative because probably the negative component is more. So you will write down high hydration enthalpy. High hydration enthalpy. For this also the answer was same. For zinc and Mn, the answer is low ionization. For nickel, it is high hydration enthalpy. High hydration enthalpy for this one. Okay, because Ni2 plus is smaller size cation. So this will get more hydrated. Fine. So first what we have discussed till here, children, if you check your NCERT book, we have discussed that E0 trend of M2 plus / M. So out of that, this or this, which one is more stable? So that is what I told you in the beginning. What is electrode potential? It's telling us which oxidation state is more stable for that particular metal. Okay. Please make note of whatever I'm explaining side by side. Now another thing you'll find in your book is that trend of that E0 M3 plus / M2 plus. Means out of 2 and 3, which is more stable? That we are going to discuss. Okay, now let's talk about scandium. You can write for these two, you can just write the configuration and decide. This is, configuration is 3D. No, 2 electrons are lost, 3D1. Yes, so this configuration is argon. Actually, it's there argon and 3D1. Right? And in this one, it is only argon. So obviously for them, which is more stable? Argon configuration. So this is more stable. Okay, so you will write down, as such I told you, low value means a higher oxidation state is more stable. So let's mark that first. In this higher, this will be more stable. In this one, this will be more stable. This will be more stable. If it is high, lower oxidation state is more stable. If the value is low, then high oxidation state is more stable. So you know now out of that, the scandium 2 plus and 3 plus, this is more stable. So it will prefer being in this. Okay. And out in this, iron 2 plus configuration is 3d6 and this is 3d5. So this you can always talk in terms of the, electronic configurations. It will happily lose one more electron. So its ionization energy values will be less. Obviously, there were 2 positive values I said. Enthalpy of atomization was positive, and then it was ionization enthalpy which was positive. These 2 values were positive and the negative value was only hydration. Sum of all this was deciding that E0 value that I already told you. So lower value means it's more negative. Lower value means either this should be too high or this should be low. So in these two, you can say the ionization enthalpy values are low because it prefers losing electron and acquiring the nearest noble gas configuration. Noble gas, or in this case half-filled configuration. Okay. Now for these two, zinc and Mn, Zn3 plus / Zn2 plus, Mn3 plus / Mn2 plus, which is more stable? The lower ones. Why? You can write as per the configuration. This is 3d10 and this is 3d5. If it still loses one more electron, it will be now 3d9. It will not like to lose electron. This will be now 3d4, which is not possible. So for Zn and Mn, the values are very high. Which values I am talking about? This value. E0 M3 plus / this. Whenever you find the value is low, that means the higher it's reverse. For low value, higher oxidation state is more stable. For higher value, lower one is more stable. Suppose I ask you in this vanadium, which is more stable? Out of this vanadium 2 plus and 3 plus, which is more stable? We'll write the configuration. It is like this: scandium, titanium, vanadium. So the configuration of vanadium as such is 3d3 4s2. 4s2 actually is filled first as per the Euler's diagram or n plus L rule. So this means it is 3d3 and this means it is 3d2. Now obviously out of these two, which is more stable? 3d3. Why 3d3 is more stable? Because it is having T2G3 half filled configuration. T2G3, in terms of T2G3, it is half filled, so this is very, very stable. Got it? So I hope this point is clear, children. Right? So in this video, children, I have completed the electrode potential value of the transition elements. So please practice it well and share the video with your friends so that more students get benefited. Right? Thank you for watching.